Imagine an object in space that does the exact opposite of a black hole. Instead of pulling everything in, it violently throws everything out. Nothing can enter it. Not light, not matter, not even a single atom. Anything that tries to fall in gets repelled, pushed away by the fabric of space-time itself. This isn't science fiction. This object appears naturally in the same equations that predict black holes. The mathematics of general relativity doesn't just allow this thing to exist. It practically demands it. It's called a white hole. And here's the unsettling part. Even though Einstein's own equations produce this object as cleanly and inevitably as they produce black holes, most physicists are almost certain that white holes do not and cannot exist in the real universe. The question is why? Before we go any further, if you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Also, before we begin, we're now live on Spotify. The link's in the description if you'd like to listen to us wherever you are. Now, let's begin. Let me start with what gravity actually is, because this is where everything begins, and this is where white holes come from. For most of human history, gravity was understood through Isaac Newton's framework. Newton, in 1687, published his law of universal gravitation. It was simple and elegant. Every object with mass attracts every other object with mass. The strength of that attraction depends on how massive the objects are and how far apart they are. Double the distance, and the force drops to 1/4. Triple the distance and it drops to 1/9. This law worked beautifully. It predicted the orbits of planets with remarkable precision. It allowed astronomers to calculate the trajectories of comets and the tides of the oceans. For over 200 years, Newton's gravity was considered essentially perfect. But there was a problem hiding inside it. Newton's gravity was a force that acted instantly across any distance. If the sun suddenly vanished right now, Newton's equation said Earth would immediately fly off in a straight line. Not after 8 minutes, when we would see the sun disappear. Immediately. Instantaneously. Faster than light. Newton himself was deeply uncomfortable with this. He called it action at a distance and admitted he had no explanation for how it worked. He just knew the math gave the right answers. For 2 centuries, physicists lived with that discomfort because the predictions were so incredibly accurate that nobody could argue with the results. Then, in 1915, Albert Einstein published something that changed everything. His general theory of relativity didn't just tweak Newton's gravity. It replaced the entire concept from the ground up. Einstein showed that gravity is not a force at all. It's geometry. Here's what that means. Space and time are not separate things. They're woven together into a single fabric called space-time. And massive objects bend this fabric. They curve it, warp it. The more massive the object, the deeper the curve. When you drop a ball, it doesn't fall because some invisible force is pulling it toward the ground. It falls because Earth's mass has curved the space-time around it, and the ball is simply following the straightest possible path through that curved space-time. That path happens to lead toward Earth's center. Think of it like this. Imagine a stretched rubber sheet, pulled tight and perfectly flat. Now, place a heavy bowling ball in the center. The sheet sags around the bowling ball, creating a curved depression. If you roll a marble across that sheet, it won't travel in a straight line anymore. It will curve toward the bowling ball, following the shape of the deformed surface. That's roughly what massive objects do to space-time. They create curves, and everything else, including light itself, follows those curves. This was a radical departure from Newton. Newton said gravity is a force. Einstein said gravity is the shape of spacetime itself. Matter tells spacetime how to curve, and curved spacetime tells matter how to move. He wrote this down as Einstein's field equations, the mathematical foundation of general relativity. They describe exactly how matter and energy curve spacetime, and how that curvature dictates the motion of everything within it. These equations are extraordinarily powerful. They predict things Newton's gravity never could. They predict that time runs slower in stronger gravitational fields. This has been measured directly with atomic clocks. GPS satellites orbiting Earth have to account for this effect. If they didn't, your navigation would drift by several kilometers within just a few hours. The fact that GPS works at all is direct proof that Einstein was right about how gravity warps time. Einstein's equations also predict that light bends around massive objects. This was confirmed during a solar eclipse in 1919, when astronomers observed that stars near the sun appeared to shift position because the sun's gravity was bending their light. This observation made Einstein world famous overnight. His theory wasn't just elegant mathematics, it matched reality in ways that Newton's gravity couldn't. But here's what matters for our story tonight. Einstein's field equations are incredibly difficult to solve. They're a system of 10 interlinked equations, each one fiendishly complex, each one tangled with the others. Einstein himself could only find approximate solutions. He could describe what gravity does in weak fields, near ordinary objects, but he couldn't find an exact solution describing what happens around a truly massive, compact object where gravity becomes overwhelming. Then, in 1916, just months after Einstein published his theory, a German physicist and astronomer named Carl Schwarzschild did something remarkable. Schwarzschild was serving on the Eastern Front of World War I at the time, calculating artillery trajectories for the German army while enduring the brutal conditions of trench warfare. And somehow, between artillery calculations, on the front lines of a war, he found the first exact solution to Einstein's field equations. Schwarzschild's solution described the space-time around a perfectly spherical, non-rotating, uncharged mass. A simple, idealized object. No spin, no electric charge, just mass and perfect symmetry. It was the simplest possible scenario you could imagine. And despite that simplicity, this solution revealed something nobody expected. Something that would take physicists half a century to fully understand. Schwarzschild's math showed that for any given mass, there exists a critical radius. If all the mass was somehow compressed within that critical radius, something extraordinary happens to the fabric of space-time. At the radius, space-time curves so severely that it forms a boundary, a point of no return. Cross that boundary moving inward and you can never come back out. Not because some force is holding you in place, not because a wall blocks your path, but because space-time itself is curved so dramatically that all possible paths, every direction you could travel, including the path light would take, all of them lead further inward. There is no outward direction anymore. Space-time has closed behind you like water closing over a sinking stone. This boundary is what we now call the event horizon, and the object it encloses is what we now call a black hole. But here's the thing. When Schwarzschild first published his solution, nobody understood what it actually meant. Not even Einstein. The mathematics showed something strange happening at the event horizon. Certain terms in the equations blew up to infinity at that boundary. They became mathematically undefined, producing divisions by zero and other signals of breakdown. Most physicists, including Einstein himself, assumed this meant the solution was falling apart at that point. They thought the event horizon was a physical impossibility, a sign that nature would never actually allow matter to compress that far. The math was producing nonsense, they believed, and that nonsense was nature's way of saying, stop, this can't happen. Einstein spent years arguing that black holes couldn't really form in the physical universe. He published a paper in 1939 specifically trying to prove that matter could never collapse past the critical radius. He was convinced the mathematics was producing a physically meaningless result, a quirk of the equations rather than a genuine prediction about reality. He was wrong, but it took decades to figure that out. In the same year Einstein published his objections, two other physicists, J. Robert Oppenheimer and Hartland Snyder, published a paper showing that a massive star which exhausts its nuclear fuel has nothing to stop it from collapsing under its own gravity. Once the fuel runs out and the outward pressure disappears, gravity wins. The star shrinks. It contracts past the critical radius. The event horizon forms, and the collapse continues all the way down to a point of infinite density called a singularity. Oppenheimer and Snyder showed that black holes aren't just mathematical curiosities. They're physical inevitabilities for stars above a certain mass. When a big enough star dies, it doesn't just fade away, it falls into itself and becomes something the universe had never seen before. But confusion about the event horizon persisted for years. That mathematical blow-up seemed to suggest something genuinely physical was happening there. It wasn't until the late 1950s and early 1960s that physicists understood the truth. The blow-up is what mathematicians call a coordinate singularity. It's an artifact of the coordinate system being used, not a real property of space-time. Let me explain what that means because it's absolutely crucial for understanding white holes. Imagine you're standing at the North Pole of Earth. Now try to describe your position using latitude and longitude. Your latitude is 90 degrees north, but what's your longitude? It could be anything. 0 degrees, 45 degrees, 180 degrees. Every line of longitude converges at the pole, so longitude becomes meaningless there. If you were using a mathematical framework that relied on longitude to describe the surface, your equations would break down at the North Pole. They produce infinities and undefined values. They'd seem to be telling you that something physically dramatic is happening at that location. But the North Pole isn't a special physical place. Earth's surface is perfectly smooth and continuous there. There's nothing weird about standing at the North Pole. No wall, no edge, no breakdown of the ground beneath your feet. The problem is entirely with the coordinate system you chose. Pick a different coordinate system, one that doesn't rely on longitude, and the North Pole is completely ordinary, unremarkable, just another point on the surface. The same thing happens with the Schwarzschild solution at the event horizon. The coordinates Schwarzschild used, which are based on the kind of measurements a distant observer would make, break down at the horizon. They produce infinities, but space-time itself is perfectly smooth and continuous there. If you were falling through the event horizon, you wouldn't notice anything special happening at that exact moment. Space and time would feel normal around you, at least locally. You might not even realize you'd crossed the point of no return until you tried to turn around and found that you couldn't. This realization was groundbreaking. It meant that the event horizon isn't a wall or a barrier in any physical sense. It's a one-way boundary. Absolutely. Once you cross it, you can never come back out. But it's not a place where physics breaks down. It's just a place where one particular set of coordinates breaks down. To see what's really happening at and beyond the event horizon, physicists needed better coordinates. Over the years, several were developed. Arthur Eddington found a set that partially removed the problem. David Finkelstein found another that made the one-way nature of the horizon crystal clear. Each new coordinate system peeled away another layer of confusion, revealing that space-time continues smoothly through the horizon rather than ending there. But the most revealing coordinates came from two physicists working independently. Martin Kruskal, an American mathematician, and George Sekeres, a Hungarian-born Australian mathematician. In 1960, they published coordinate systems that didn't just remove the false infinity at the event horizon. They revealed the complete structure of the Schwarzschild solution for the first time in its full mathematical glory. And what they found was shocking. When you write the Schwarzschild solution in Kruskal-Sekeres coordinates, you don't just get a black hole. You get something far more complex and far stranger. The full mathematical structure contains 4 distinct regions of spacetime. Not 1, not 2, 4. And these 4 regions are connected to each other in ways that nobody had anticipated. Region 1 is the exterior. That's our universe. The normal spacetime outside the event horizon where stars shine, planets orbit, and we live our lives. This is the region that Schwarzschild's original coordinates describe perfectly well. Region 2 is the interior of the black hole. Once you cross the event horizon inward from Region 1, you enter Region 2. Here, the very nature of space and time transforms. The roles of space and time essentially swap. The singularity at the center isn't a point in space that you might steer around or avoid. It becomes a moment in your future. No matter which direction you move, no matter how powerful your engines, no matter how hard you try, you will reach the singularity. It's not a place you fall toward. It's a future you cannot escape. Every path leads there. But then, there are 2 more regions. And this is where the story takes its strangest turn. Region 3 is a mirror image of Region 2, but reflected in time. It's an interior region with its own singularity. But instead of being a place where everything falls inward and gets crushed, it's a place where everything erupts outward. Matter and light don't fall into this region's singularity. They emerge from it. They're born from it. And they fly outwards, crossing a boundary that works like an event horizon in reverse. You can leave this region, matter and light come pouring out of it, but you can never enter it. Nothing can cross that boundary going inward. It's a cosmic exit with no entrance. This is the white hole. Region 4 is a second exterior region, a separate expanse of space-time that looks like another universe entirely. Matter that exits the white hole in Region 3 can end up in either Region 1, our universe, or Region 4, this other exterior. These 4 regions together are the complete picture. They're the full mathematical content of the Schwarzschild solution when you don't artificially cut the math short. The equations don't just produce a black hole, they produce a black hole, a white hole, 2 separate exterior regions of space-time, and connections between all of them. All from the same equations, all from the same solution, all from the same theory of gravity that has been confirmed over and over again by experiments and observations. Now, I need to explain what it means to say a white hole is the time-reversed version of a black hole, because this is the key to understanding why the mathematics produces this object so naturally and so inevitably. Think about a simple physical process. You drop a glass. It falls, hits the floor, and shatters into 100 pieces. Now imagine filming that moment and playing the film in reverse. You see 100 shards of glass leap up from the floor, fly through the air, and reassemble into a perfect unbroken glass that lands neatly in your hand. Every single frame of that reversed film obeys Newton's laws of motion. Every collision between glass shards, every trajectory, every transfer of energy is physically valid. The reversed film is a perfectly legitimate solution to the equations of classical mechanics. General relativity has the same property. Einstein's field equations are time-symmetric. If you have a solution that describes something happening forward in time, you can reverse the direction of time and get another perfectly valid solution. The equations don't prefer one direction over the other. They are completely indifferent to whether time runs forward or backward. A black hole is a region where space-time is curved so severely that everything falls inward past a one-way boundary. The event horizon only works in one direction. You can cross it going in, but you can never cross it coming out. The singularity lies in your future once you've entered. Now reverse time. Inward becomes outward. The future singularity becomes a past singularity, something that existed before you arrived, rather than something you're doomed to hit. Instead of everything falling in and nothing escaping, everything comes out and nothing can get in. The one-way boundary still exists, but now it works in the opposite direction. You can cross it going out, but you can never cross it going in. That's a white hole. It's not a separate theory. It's not a new set of equations that someone invented. It's the same solution, the very same mathematics, viewed with time running in the opposite direction. The math is completely self-consistent. There's no error, no trick, no sleight of hand. If you accept that the Schwarzschild solution describes a black hole when time runs forward, then you must accept that it also describes a white hole when time runs backward. The equations don't care which direction you choose. This is what makes white holes so mathematically compelling and so difficult to simply dismiss. They don't require new physics. They don't require exotic matter or unknown forces or speculative dimensions. They arise directly, inevitably, inescapably from the same theory of gravity that predicts black holes. And we know black holes are real. We've observed them, we've detected the gravitational waves produced when two black holes spiral together and merge through the LIGO experiment in 2015. We've photographed the shadow of a supermassive black hole in the galaxy M87 through the Event Horizon Telescope in 2019. We've tracked stars orbiting Sagittarius I star, the supermassive black hole at the center of our own Milky Way, confirming its existence beyond any reasonable doubt. General relativity's predictions about black holes have been confirmed again and again and again. So here's the uncomfortable question. If the same equations that correctly predict black holes also predict white holes, can we simply ignore the white hole prediction? Can we just wave our hands and say, that part of the math doesn't count? It's not that simple. In physics, you don't get to cherry pick which predictions of a theory you accept. If a theory makes 10 predictions and 9 match observations perfectly, you have to take the 10th seriously. You investigate it. You ask why it might or might not correspond to something in the real universe. General relativity has been tested more rigorously than almost any theory in the history of science. It predicts the bending of light around massive objects. Confirmed. It predicts the precise orbit of Mercury, which Newton's gravity got slightly wrong. Confirmed. It predicts that time slows down in gravitational fields. Confirmed repeatedly, with extraordinary precision. It predicts gravitational waves. Confirmed. It predicts black holes. Confirmed through multiple independent lines of evidence. Every prediction of general relativity that we've been able to test has turned out to be correct. This theory has an almost perfect track record, and this same theory with this almost perfect track record also predicts white holes. Now, this doesn't necessarily mean white holes must exist in the real universe. Mathematical prediction and physical existence are not the same thing. An equation can have solutions that are mathematically valid, but physically unrealized. But it does mean we have to take the prediction seriously enough to understand exactly why white holes probably don't exist, rather than just dismissing them with a shrug. There's one more critical thing you need to understand about the Schwarzschild solution and its white hole. And this point is essential because it reveals the first serious crack in the white hole's claim to physical reality. The complete Schwarzschild solution, the one that contains all 4 regions including the white hole, describes an eternal black hole, not a black hole that formed at some point in time from a collapsing star. An eternal one. A black hole that has existed for all of time and will continue to exist for all of time. It was never born. It will never die. It has no origin, no history, no formation process. It simply is. In this eternal solution, the white hole sits in the infinite past. It has always been there, ejecting matter and light outward since the beginning of time. The black hole sits in the future, swallowing matter and light forever. The 2 exterior regions exist side by side, connected through the interior regions, for all of eternity. But here's the problem. Real black holes aren't eternal. They form. They have a beginning. A massive star lives for millions or billions of years, fusing hydrogen into helium in its core, then helium into carbon, then carbon into heavier elements, until finally it runs out of fuel. Its core collapses. Gravity overwhelms everything. An event horizon forms. Before the star collapsed, there was no black hole. After the collapse, there is one. The black hole has a birthday. It came into existence at a specific moment in time through a specific physical process. When you actually model the formation of a real black hole from a collapsing star, as Oppenheimer and Snyder did back in 1939, something important happens to the full Schwarzschild geometry. The white hole region and the second exterior region disappear entirely. They get replaced by the interior of the collapsing star. Before the collapse, there was ordinary spacetime, just a massive star burning through its fuel. No white hole lurking in the past. No second universe hiding behind a mathematical curtain. The white hole only exists in the eternal, idealized version of the solution. The version that doesn't correspond to any real astrophysical object or any real physical process that we know of. This is a subtle but absolutely crucial point. The full 4-region structure of the Schwarzschild solution is mathematically beautiful. It's logically consistent. It's entirely valid as a solution to Einstein's equations, but it describes a situation that doesn't match our universe. Real black holes form from real processes. They have histories. They have origins. And those histories, those origins, don't include white holes. Remember the film of the shattering glass played in reverse? Every frame obeyed Newton's laws. The reverse process was a perfectly valid solution to the equations of motion, but you would never expect to see it happen in real life. The reverse process is allowed by the fundamental equations, but effectively forbidden by something else, something the basic equations of motion don't capture. In the case of the glass, it's the second law of thermodynamics, the overwhelming tendency of disorder to increase that makes the shattering overwhelmingly more likely than the unshattered glass reassembling itself from scattered shards. Something similar appears to be happening with white holes. The equations of general relativity allow them. The time symmetry of those equations guarantees that if black holes are valid solutions, white holes must be valid solutions too. But the equations of general relativity don't include everything about the universe. They don't include thermodynamics. They don't include quantum mechanics. They don't include the specific initial conditions that our universe started with. And when you start to add those things back into the picture, when you ask not just what the equations allow, but what the universe actually does, white holes start to look very different from their black hole counterparts. Black holes are robust. They form naturally and readily from collapsing matter. They're stable once they exist. They grow by consuming material from their surroundings. The universe produces them abundantly. We've found evidence for millions of them scattered across the cosmos, from stellar mass black holes born in supernova explosions to supermassive black holes sitting at the hearts of galaxies. White holes, by contrast, seem to require conditions that the universe never provides. They need to have existed from the infinite past, embedded in a perfectly eternal geometry. Or they need to form through some physical process that nobody has ever identified. They're the reverse of a natural process, and nature, it appears, only runs the film in one direction. This is where we stand after examining the mathematics. The equations of general relativity, one of the most successful and thoroughly tested theories in the history of science, produce white holes just as naturally and inevitably as they produce black holes. The math makes absolutely no distinction between the two, but the universe, it seems, does. The universe is full of black holes and apparently empty of white holes. The math says they should exist. Reality says they don't appear to. Understanding exactly why the universe refuses to produce these objects, why reality breaks the perfect symmetry of the equations, requires looking beyond the mathematics itself and into the deeper physics that the equations alone don't capture. And that's exactly where we're heading. Now that we know where white holes come from mathematically, let's try something more difficult. Let's try to imagine what one would actually be like. Not as an equation on a chalkboard, not as a diagram in a physics textbook, but as a real object sitting out there in space. Something you could observe through a telescope. Something you could send a spacecraft toward. Something that exists in the physical universe the way a star or a planet or a black hole exists. Because when you actually work through the physics of how a white hole would behave, when you trace out its properties one by one and compare them to everything else we know about the universe, you quickly realize that a white hole would be the single strangest object that could possibly exist. Stranger than black holes, stranger than neutron stars, stranger than anything nature has ever produced, as far as we can tell. Let me start with the most fundamental property. A black hole has an event horizon that works as a one-way door inward. Anything can cross that boundary heading toward the singularity, but nothing can ever cross it heading outward. That's what makes a black hole black. Light cannot escape, so you see nothing coming from behind the horizon. A white hole has an event horizon too, but its horizon works in exactly the opposite direction. It's a one-way door outward. Matter and light come pouring out through the horizon, erupting into the surrounding universe, but nothing can cross that boundary heading inward. Not a photon, not a neutrino, not a single atom. You could aim a laser beam directly at the white hole's horizon, and that beam would never reach it. You could fire a rocket at full thrust straight toward it, and the rocket would be deflected, pushed away, turned aside. Not by a force in the traditional sense, not by some kind of shield or barrier, but by the curvature of space-time itself. Think about what this means. Near a black hole, if you're close enough and you stop firing your engines, you fall in. Gravity pulls you toward the horizon. You have to actively work, actively spend energy to stay away from a black hole. The closer you get, the harder you have to work to resist. And past a certain point, no amount of work will save you. Near a white hole, the opposite is true. If you're close to the horizon and you stop firing your engines, you don't fall in. You move away. Space-time itself is shaped so that all paths near the white hole horizon lead outward. No matter how hard you tried, no matter how powerful your engines, you could never reach it. The horizon is unreachable from the outside. It's there. You can calculate exactly where it is, but you can never touch it. This is already bizarre. Every object we know of in the universe allows things to approach it. Stars allow matter to fall onto their surfaces. Planets allow meteors to crash into them. Even black holes, the most extreme objects we know, allow things to fall in. That's essentially all black holes do. They accept matter and energy from their surroundings. A white hole refuses. It is the only theoretical object in all of physics that categorically, absolutely, fundamentally cannot be approached. Now let's talk about what comes out of a white hole, because this is where things get truly strange. Matter and light emerge from the white hole's singularity and pass outward through its horizon into the surrounding universe. They appear from behind the horizon the way sunlight appears from behind a hill at dawn. Except that, with the sun, you understand where the light comes from. The sun is a ball of fusing hydrogen, converting mass into energy through nuclear reactions you can describe and predict. The light has a cause. It has an origin story. There's a physical mechanism that produces it. With a white hole, there is no mechanism. The matter and light that emerge from the white hole's singularity have no cause that any outside observer can identify. They don't come from some process happening inside the white hole, the way fusion happens inside a star. They emerge from the singularity, a point of infinite density and infinite curvature where the known laws of physics break down completely. The singularity isn't a place where something is happening, it's a place where our understanding of physics ends. It's a boundary beyond which we cannot calculate, cannot predict, cannot even meaningfully describe what is occurring. So the matter that erupts from a white hole is matter without a history. It has no past. It has no origin. It simply appears. One moment it doesn't exist, at least not in any way we can describe. The next moment it is bursting outward through the horizon and into the universe. It is uncaused matter, spontaneous creation from a point where physics itself has no answers. This violates something very deep about how we understand the universe. In physics, events have causes. Effects follow from prior conditions. Every particle has a history. Every photon was emitted by something. Every explosion was triggered by something. Cause and effect is the very foundation on which physics rests. A white hole breaks this chain. The matter it produces has no prior cause. It appears from a singularity that is not inside the universe, but is rather a boundary of the universe. A place where the mathematical description of spacetime simply ends. You cannot ask what happened before the matter appeared, because the singularity isn't a before, it's an edge. It's a wall in time beyond which the concept of before loses meaning. Now, let's think about what a white hole would look like to a distant observer. Someone watching through a powerful telescope from a safe distance. What would they see? They would see an object radiating matter and energy outward in all directions. Light would stream away from it. Particles would fly outward at tremendous speeds. It might look superficially like an explosion, like a supernova or a gamma ray burst. Something violently energetic that's throwing material into space. But there's a critical difference. Explosions stop. A supernova detonates and then it's over. The debris expands, cools, and fades. A gamma ray burst flashes and then dims. These events have beginnings and endings. They're transient. They happen and then they're done. A white hole, at least in the idealized eternal version from the Schwarzschild solution, doesn't stop. It keeps producing matter and energy. It keeps radiating outward. It's not an event. It's a permanent feature of space-time. It's always been there, always spewing material, never running out, never fading. It has no fuel source because it doesn't need fuel. The matter comes from the singularity, which is not a fuel reservoir, but a mathematical boundary where the laws of physics offer no explanation. An observer would also notice something important about the energy coming from a white hole. The matter and radiation emerging from the white hole's singularity would originate from a region of extreme density and curvature, carrying potentially enormous energy at their point of origin. But the exterior gravitational field of a white hole is identical to that of a black hole with the same mass. This means that light traveling outward from a white hole loses energy climbing out of the gravitational well. Its wavelength stretches. It becomes redshifted. This is called gravitational redshift, and it's one of the classic predictions of general relativity, confirmed by experiments on Earth and observations of stars and galaxies. Light climbing out of a gravity well arrives at your eyes with less energy than it had when it started. So light from a white hole would be gravitationally redshifted on its journey to a distant observer, just as light from any massive object is. The crucial difference is the source. The radiation originates from the singularity, a region of infinite curvature where energies could be unimaginably high. Even after gravitational redshift extracts energy during the outward journey, the initial energy could be so extreme that the remaining signal is still tremendous. A white hole could potentially be one of the brightest objects in the universe, radiating furiously across every wavelength from radio waves to gamma rays. From a distance then, a white hole might resemble a quasar, one of those incredibly luminous objects at the centers of distant galaxies, powered by supermassive black holes consuming vast amounts of matter. In fact, in the early days of quasar research in the 1960s, before astronomers understood that quasars were powered by black holes, some physicists genuinely proposed that quasars might be white holes. They saw these absurdly bright objects pouring energy into space and thought maybe, just maybe, they were seeing matter emerging from white hole singularities. That hypothesis was eventually abandoned. The quasar observations matched the predictions of black hole accretion far too well. The matter swirling around quasars forms accretion disks that radiate in predictable patterns at predictable wavelengths. All of this is perfectly explained by matter falling toward a black hole, not by matter erupting from a white hole. But the fact that physicists even consider the idea tells you something important. White holes aren't just abstract mathematical curiosities. If they existed, they would produce real, observable effects. They would be visible. They would interact with the surrounding universe. The reason we don't think they exist isn't that they would be invisible or undetectable. It's that we've never seen anything that behaves the way a white hole should behave. We've looked, we found nothing. Now here's where the story gets even more fascinating. Because hidden in the full Schwarzschild geometry, in that 4-region structure described by Schwarzschild, CK-Resh coordinates, there's a connection between the black hole and the white hole that has captured the imagination of physicists and science fiction writers alike. This connection is called an Einstein-Rosen bridge, and it's what most people mean when they use the word wormhole. Let me walk you through how it works. And more importantly, let me explain why it absolutely does not work the way you might think. In the full Schwarzschild geometry, Region 1 is our exterior universe, and Region 4 is a second exterior universe. Between them sits the black hole interior and the white hole interior. Now, if you take a snapshot of this geometry at a single moment in time and examine its spatial structure, you find something remarkable. The two exterior regions are connected by a narrow throat, a bridge of space-time linking two otherwise separate universes. This throat passes through the interior region, connecting one side to the other through a tunnel in the fabric of space-time. This connection was first noticed by Albert Einstein and Nathan Rosen in 1935. They were studying the Schwarzschild solution and realized that the geometry contained this bridge between two separate regions. They published a paper describing it, and the concept has been called an Einstein-Rosen bridge ever since. Actually, the idea goes back even further. An Austrian physicist named Ludwig Flamm had noticed a similar geometric property as early as 1916, the same year Schwarzschild published his original solution. But Flamm's work didn't attract much attention at the time. The Einstein-Rosen bridge is the origin of the wormhole concept. It's the mathematical seed from which decades of science fiction grew. Stories about tunnels through space, shortcuts between distant stars, portals to other universes, all of them trace back, ultimately, to this geometric feature of the Schwarzschild solution. But here's what science fiction almost always gets wrong. The Einstein-Rosen bridge in the Schwarzschild geometry is not traversable. You cannot travel through it. Not in practice, not even in principle. The bridge doesn't stay open long enough for anything to pass through. Let me explain why. The Einstein-Rosen bridge is dynamic. When you take that snapshot I described and look at the spatial geometry at one moment, the bridge exists. But take another snapshot a moment later and the throat has gotten narrower. Another moment after that, narrower still. The bridge is pinching off. The bridge opens, reaches its maximum width, and then collapses and pinches shut so quickly that nothing, not even light, traveling at the fastest speed possible in the universe, can pass from one side to the other before the bridge closes. The throat snaps shut faster than any signal could traverse it. If you tried to fly a spacecraft through an Einstein-Rosen bridge, the bridge would collapse around you before you reach the other side. You wouldn't emerge in another universe. You'd be crushed in the collapsing throat or swallowed by the singularity. This is not a matter of engineering. It's not a problem you could solve with better technology or faster engines. The bridge collapses because of the fundamental geometry of space-time. The same equations that create the bridge also guarantee its destruction, and no amount of cleverness can change the equations. Now, you might wonder whether there are other kinds of wormholes that might be traversable, and the answer is yes, in theory, but they require something that may not exist. In 1988, physicists Kip Thorne and Michael Morris showed that a traversable wormhole could exist if it were threaded with what's called exotic matter with negative energy density. This exotic matter would counteract the gravitational tendency of the wormhole to collapse. It would hold the throat open long enough for something to pass through. But exotic matter is deeply problematic. No one has ever observed it. There's no evidence it exists in nature. Some calculations in quantum field theory suggest that tiny amounts of negative energy might be possible under very specific circumstances, but the amounts needed to stabilize a wormhole are enormous, possibly more energy than exists in the observable universe. Most physicists consider traversable wormholes to be a fascinating theoretical exercise, but not a realistic possibility. And crucially, even if traversable wormholes could somehow exist, they would be different objects from the Einstein-Rosen bridge in the Schwarzschild solution. They would require different physics, different matter, different conditions. The white hole geometry doesn't give you a traversable wormhole. It gives you a bridge that self-destructs before you can use it. So let me be very clear about the distinctions here, because they're important and they often get blurred in popular science. A black hole is a region of space-time where gravity is so strong that nothing can escape once it crosses the event horizon. We know black holes exist. We've observed them. They form from collapsing stars. They sit at the centers of galaxies, and they merge together producing gravitational waves we can detect. A white hole is the time-reversed counterpart of a black hole. It's a region of space-time where nothing can enter, and everything comes out. It appears in the mathematics of general relativity as naturally as black holes do. But we have never observed one, and there are strong reasons to believe they don't exist in the real universe. A wormhole, specifically an Einstein-Rosen bridge, is a geometric connection between two separate regions of space-time that appears in the complete Schwarzschild solution. It is not traversable. It opens and collapses faster than anything could pass through. A traversable wormhole is a hypothetical object that would require exotic matter to hold open. It is a different thing from an Einstein-Rosen bridge. It has never been observed and may be physically impossible. In science fiction, all four of these concepts get mixed together into a single idea. A portal you can fly through to reach another part of the universe or another universe entirely. But in physics, they are distinct, and the distinctions matter enormously. Let me add one more layer to this picture, because there's something about white holes that makes them different from every other object in astrophysics. And it goes beyond just the direction of their event horizons. Every astrophysical object we know of interacts with its environment. Stars pull in gas from nearby clouds and emit light and radiation. Planets absorb sunlight and reflect some of it back. Black holes consume matter from accretion disks and sometimes produce powerful jets of material along their polar axes. Neutron stars emit beams of radiation as they spin. Even the empty vacuum of space interacts with quantum fields, producing virtual particles that flicker in and out of existence. All of these objects participate in a two-way relationship with the universe. They take in something, matter or energy or both, and they give something back. They are part of the cosmic ecosystem. They affect their surroundings and are affected by them. A white hole breaks this reciprocity. It gives, but it does not receive. It outputs matter and energy, but it cannot accept any input. It radiates, but it cannot absorb. It is a cosmic one-way valve, and that one-way valve points outward. This creates a paradox that goes beyond simple strangeness and gets into genuine logical difficulty. Consider what happens when the matter ejected by a white hole encounters other matter in the surrounding universe. Gas flies outward from the white hole. It collides with interstellar gas, with dust, with the debris of old stars. These collisions produce shock waves, heat, radiation. The ejected material piles up around the white hole, forming a shell or a cloud. This cloud grows denser as more material accumulates. Now, all the accumulated matter has mass, and mass creates gravity. The shell of matter around the white hole is gravitationally attracted back toward the white hole. It wants to fall inward. Gravity is pulling it toward the white hole's horizon. But the white hole's horizon won't let anything in. The matter can't cross the horizon heading inward. It pushes against the boundary of space-time, and space-time pushes back. So what happens? The matter piles up just outside the horizon. It gets denser and denser. The pressure builds. The temperature rises. Energy concentrates in an ever thinner shell around the white hole's boundary. And this creates an unstable situation. A situation that, as we'll see later, has devastating consequences for the white hole's very existence. But even setting aside that instability, there's something conceptually disturbing about a white hole. It's an object that produces things without consuming anything. It creates matter and energy from its singularity without any input, without any fuel, without any mechanism that outside physics can describe. This isn't just unusual. It's unique. Nothing else in the known universe works this way. Every other source of energy we've ever found involves a transformation. Nuclear fusion converts hydrogen into helium and releases energy. Chemical combustion converts fuel and oxygen into heat and exhaust. Gravitational collapse converts potential energy into kinetic energy and radiation. In every case, something goes in and something comes out. Conservation laws are obeyed. Energy doesn't appear from nothing. A white hole seems to violate this principle at the deepest level. The energy pouring out of it has no identifiable source. The matter emerging from it has no identifiable origin. It's creation without cause, output without input, effect without a proportional and traceable mechanism. Now, a careful physicist would point out that the energy isn't truly coming from nothing. It's coming from the singularity, from whatever physics operates at that point of infinite density and curvature. And since we don't have a complete theory of quantum gravity, since we don't know how physics works at singularities, we can't definitively say that conservation laws are being violated. Maybe the singularity has some reservoir of energy we don't understand. Maybe the matter emerging from a white hole is being produced by processes that a future theory of quantum gravity will describe. That's true. But it doesn't make white holes less strange. It just pushes the strangeness to a deeper level. Instead of saying a white hole violates conservation laws, we say a white hole requires physics we don't yet understand. And until we have that physics, we can't fully explain where the matter comes from. There's also the question of predictability. One of the most powerful features of physics is that it allows you to predict the future from the past. If you know the positions and velocities of all the particles in a system right now, The laws of physics tell you where they'll be at any future time. This is called determinism, and while quantum mechanics introduces some fundamental randomness at the subatomic level, the broad principle holds. The present determines the future. A white hole undermines this principle. The matter emerging from a white hole singularity is not determined by anything in the exterior universe. It doesn't come from the past of the universe we live in. It comes from the singularity, which is not part of the space-time that our physics describes. The singularity is a boundary, an edge, a place where the mathematical description of space-time terminates. What comes out of that boundary is not predictable from any information available in the exterior universe. This means that a white hole introduces genuine unpredictability into the universe, not the quantum mechanical uncertainty that we're used to, where probabilities can at least be calculated, but fundamental, absolute unpredictability. Matter appears from the singularity, and there is no way, even in principle, to predict what that matter will be, how much of it there will be, or when it will appear. The universe becomes, in a very real sense, incomplete. There are facts about it that cannot be derived from other facts. There is information entering the universe from outside the universe, from a place that is not described by any physics we possess. Roger Penrose, the British mathematician and physicist, formalized concerns like this into what he called the cosmic censorship hypothesis. Penrose proposed that singularities in the real universe are always hidden behind event horizons. They're always cloaked by a black hole's boundary, so that the unpredictability they introduce is quarantined from the rest of the universe. What happens inside a black hole stays inside a black hole. The singularity can be as wild and unpredictable as it wants, because nothing that happens there can affect the outside universe. A white hole violates cosmic censorship in spirit, if not in technical detail. The white hole's singularity is hidden behind its own horizon, yes, but that horizon points the wrong way. Matter comes out. The singularity's output pours into the universe. So while the singularity itself might be technically hidden, its effects are very much public. The unpredictable matter it produces enters the universe and interacts with everything around it. The quarantine fails. Let me paint one final picture of a white hole to drive home just how strange this object would be. Imagine you're an astronaut approaching what you've been told is a white hole. You fire your engines and move toward it. As you get closer, you see light streaming towards you from its direction. Particles and radiation are flying outward. You feel the gravitational pull diminishing rather than increasing as you approach. You push harder, accelerating toward the horizon. But no matter how hard you push, you never get closer. Space-time curves away from you. The horizon recedes like a mirage in a desert. You're expending enormous amounts of energy, burning fuel at a furious rate, but the distance between you and the horizon doesn't shrink. The geometry of space-time is arranged so that the horizon is unreachable from the outside. Every path you could take curves away from it. You are being denied entry to a place that is actively throwing things at you. Meanwhile, matter is erupting from the white hole and streaming past you. Particles fly by at tremendous velocities. Light washes over your spacecraft. Energy pours past you in all directions. You're being pelted by the output of an object you cannot touch, cannot reach, and cannot influence in any way. You can see it. You can detect its output. You can feel the effects of the matter it produces, but you cannot interact with it. You cannot send anything toward it. You cannot signal it, probe it, or in any meaningful sense, reach it. Compare this to any other object in the universe. You can land on a planet, you can orbit a star, you can fall into a black hole, you can smash into an asteroid. Every other object in the cosmos allows you to approach and interact with it, even if that interaction destroys you. A white hole is the one object that refuses all contact. It is absolutely, utterly isolated from the rest of the universe in terms of incoming influence, while simultaneously flooding the universe with its output. This is the white hole, the strangest object that general relativity can produce, an object that ejects matter and light without cause, that refuses all incoming matter and energy, that breaks the chain of causation, that introduces unpredictability, and that exists in the mathematics as naturally as the black holes we've confirmed are real. It is an object that the equations demand, but that the universe, it seems, wants nothing to do with. And now we need to understand why. We need to understand what it is about the real universe, about the actual physical world rather than the ideal mathematical world, that makes white holes so profoundly unlikely. We need to understand why nature runs the film in only one direction. Why the time symmetry of Einstein's equations, the perfect mathematical balance between black holes and white holes, is broken so completely and so decisively by the universe we actually inhabit. So now we have a picture of what a white hole is. We know it comes from the same equations that produce black holes. We know it would behave as a reversed black hole, ejecting matter and energy while refusing to accept anything from the outside universe. We know it sits naturally in the full Schwarzschild solution as the time-reversed partner of the black hole region. And we know it would be profoundly strange, an object unlike anything else in all of astrophysics. But knowing what a white hole is doesn't tell us whether one actually exists. And this distinction, the gap between what the math allows and what the universe actually produces, is one of the most important ideas in all of physics. Because the universe is not obligated to produce every object that appears in an equation. Equations describe possibilities. The universe selects which possibilities become reality, and the universe, it appears, has very strong opinions about white holes. There are 4 major arguments against the existence of real white holes, and each one attacks the idea from a completely different direction. Together they form a case so overwhelming that almost no working physicist today expects white holes to exist in nature. Let's go through each one carefully. The first argument is thermodynamic, and it might be the most devastating of all because it strikes at the deepest level of how the universe operates. There's a law of physics called the second law of thermodynamics. You've probably heard of it, at least in passing. It's one of those laws that shows up everywhere, from the design of car engines to the eventual fate of the universe. But most people don't fully appreciate just how fundamental it is. The second law doesn't just describe how engines work or how heat flows, it governs the direction of time itself. It is, in a very real sense, the reason that the past and the future are different. The second law says that in any closed system, entropy, which is a measure of disorder or randomness, either stays the same or increases over time. It never spontaneously decreases. Disorder grows, things fall apart, hot objects cool down, cold objects warm up, structures decay, energy spreads out and becomes less useful. This isn't just a tendency, it's an overwhelming statistical certainty, built into the very mathematics of how large numbers of particles behave. Let me make this concrete. Imagine a box divided in half by a wall. On the left side, you have a gas. On the right side, a vacuum. Remove the wall and the gas expands to fill the entire box. Completely unsurprising. But why doesn't the gas spontaneously contract back to one side of the box? The answer is probability. There are overwhelmingly more ways for the gas molecules to be spread throughout the entire box than there are ways for them to be concentrated in just one half. The number of possible arrangements where the gas fills the whole box is so staggeringly larger than the number of arrangements where the gas occupies only half that the probability of the gas spontaneously contracting is effectively zero. Not exactly zero. Not fundamentally impossible, but so close to zero that you could wait for the entire age of the universe, trillions upon trillions of times over, and never see it happen. This is what the second law captures. Systems evolve toward the most probable states, and the most probable states are the ones with the highest entropy, the highest disorder, the most even distribution of energy. The universe runs downhill, thermodynamically speaking. It moves from ordered states to disordered states, from concentrated energy to spread out energy, from improbable arrangements to probable ones. This gives time its direction. The second law is what distinguishes the past from the future. In the past, things were more ordered. In the future, they'll be less ordered. Eggs break, but don't unbreak. Milk mixes into coffee, but doesn't unmix. Buildings crumble, but don't uncrumble. All of these everyday observations are manifestations of the second law of thermodynamics. They happen because the disordered state is overwhelmingly more probable than the ordered state. Now let's connect this to black holes. In the early 1970s, a young physicist named Jacob Bekenstein made a remarkable discovery. He showed that black holes have entropy, not just a little entropy, enormous entropy. A black hole's entropy is proportional to the area of its event horizon, and is almost always the maximum possible entropy for any object of that mass. This was a revolutionary insight. It meant that black holes are not just gravitational objects, they're thermodynamic objects. They participate in the second law of thermodynamics, just like everything else. When matter falls into a black hole, the black hole's event horizon grows, its area increases, its entropy increases, the total entropy of the universe goes up. The second law is satisfied. Everything makes sense. Stephen Hawking built on Bekenstein's work and showed that black holes have a temperature. They radiate, albeit incredibly faintly, through a quantum process now called Hawking radiation. Black holes are thermodynamic objects in every meaningful sense. They have entropy, they have temperature, they absorb heat, and they radiate. They follow the same thermodynamic laws as everything else. Now think about a white hole. A white hole is the time-reversed version of a black hole. It does everything a black hole does, but backward in time. A black hole absorbs matter and its entropy increases. A white hole ejects matter and its entropy, if we follow the time reversal logic, would have to decrease. This is the problem. A white hole represents entropy spontaneously decreasing. It represents the universe running uphill rather than downhill. It represents gas spontaneously contracting into one corner of a room. Coffee spontaneously separating from milk, an egg spontaneously unbreaking, a building spontaneously uncrumbling. The second law of thermodynamics doesn't just say these things are unlikely. It says they're so overwhelmingly improbable that they essentially never happen in the real universe. The probability of a macroscopic violation of the second law is not just small. It's smaller than any number you could write down. Smaller than 1 divided by the number of atoms in the observable universe. Smaller than 1 divided by the number of possible chess games. smaller than any meaningful quantity in all of science. A white hole, by its very nature, represents exactly this kind of violation. It's a macroscopic system whose entropy is decreasing. It's running backward. It's doing thermodynamically what playing a film in reverse does visually. And the second law says the universe doesn't run backward. Not at this scale. Not with these odds. This is why Rudolf Clausius, the German physicist who formulated the second law in the 1850s, called entropy the most fundamental quantity in all of physics. And this is why Ludwig Boltzmann, who gave entropy its statistical foundation, considered the second law to be the deepest truth about the physical world. The second law isn't just a rule about heat engines. It's a rule about the arrow of time. It's the reason things happen in one direction rather than the other. And white holes point in the wrong direction. Now, you might object. You might say, wait, general relativity's equations are time-symmetric. They don't have a built-in arrow of time. They don't know about entropy. They're perfectly happy with white holes. Isn't this a contradiction? It's not a contradiction. It's a lesson. It tells us that general relativity, powerful as it is, doesn't capture everything about the universe. The equations of general relativity describe how space-time curves in response to matter and energy. They do this brilliantly, but they don't include thermodynamics. They don't know about the second law. They don't know about entropy. They describe the geometry of the universe without describing its thermodynamic direction. The second law comes from somewhere else. It comes from the statistical behavior of enormous numbers of particles. It comes from probability. It comes from the fact that disordered states are overwhelmingly more numerous than ordered states. And when you combine general relativity with thermodynamics, when you ask not just what space-time geometries are mathematically possible, but which ones are thermodynamically consistent, white holes fail the test. They're geometrically valid, but thermodynamically forbidden. They satisfy Einstein's equations, but violate Boltzmann's statistics. The second argument against white holes is instability. And this argument is devastating in a different way, because it shows that even if a white hole somehow came into existence, it couldn't survive. Remember the picture we painted not long ago? Matter ejected by the white hole collides with the surrounding interstellar medium and accumulates around the white hole's horizon. This matter can't fall in because the horizon works as a one-way door outward. So it piles up. It forms a shell. That shell grows denser and more massive over time. But here's the critical problem. The white hole's horizon is extraordinarily sensitive to incoming matter and energy. Even the tiniest perturbation, the smallest disturbance from the outside universe, can trigger a catastrophic change. And the universe is never truly empty. Space is filled with radiation. The cosmic microwave background, the leftover glow from the Big Bang, permeates all of space at a temperature of about 2.7 degrees above absolute zero. Photons from this background radiation are everywhere, streaming through space in every direction, filling the cosmos with a faint but constant bath of electromagnetic energy. A black hole's horizon is robust against perturbations. If a photon hits a black hole's event horizon, the black hole simply absorbs it. The horizon grows very slightly larger. The black hole becomes very slightly more massive. Nothing dramatic happens. The black hole is stable. It can absorb essentially anything the universe throws at it without being destabilized. A white hole's horizon is the opposite. It is exquisitely fragile. Theoretical analyses have shown that even a single photon approaching the white hole's horizon can cause catastrophic instability. The photon cannot cross the horizon going inward, but it interacts gravitationally with the space-time around the horizon. Its energy gets concentrated and amplified near the boundary. The perturbation grows, and within an extraordinarily short time, the white hole's geometry transforms. The white hole collapses. It converts into a black hole. Think about what this means. The universe is bathed in radiation. There is no place in the cosmos that is truly empty of photons. Even in the darkest voids between galaxy clusters, there are still cosmic microwave background photons passing through, neutrinos streaming by, gravitational waves rippling through space-time. The universe is constantly, relentlessly pelting every point in space with some form of energy. A white hole placed anywhere in the real universe would be immediately bombarded by this ambient radiation. That bombardment would almost instantly destabilize it. The white hole would collapse or convert into a black hole on a timescale so short it would barely register as having existed at all. This isn't just a problem of being in a busy part of the universe. Even the emptiest voids in the cosmos contain cosmic microwave background radiation. Photons that have been streaming through space for nearly 14 billion years since the universe became transparent fill every corner. There is no hiding from this radiation. There is no refuge. The instability of white holes is so severe that many physicists consider it the most physically decisive argument against them. The thermodynamic argument tells you white holes are overwhelmingly improbable. The instability argument tells you that even if one miraculously appeared, it would destroy itself almost immediately. The universe doesn't just forbid white holes from forming, it forbids them from surviving. The third argument is about formation. Black holes exist because there is a well-understood physical process that creates them. The death of a massive star follows a predictable sequence. For millions of years, nuclear fusion holds the star up against its own weight. When that fuel is finally spent, nothing remains to resist the crushing force of gravitation. The core implodes. For remnants exceeding roughly 3 solar masses, no known force in the universe can arrest the contraction. The stellar material vanishes behind a newly formed event horizon. A black hole is born. This process is well understood. It's been modeled extensively with computer simulations. The physics at each stage, nuclear fusion, radiation pressure, gravitational collapse, the formation of the event horizon, all of it follows from known and tested laws. We've even observed the aftermath of this process. When massive stars explode as supernovae, sometimes the core that remains behind is a black hole. The results of this process are observable throughout the cosmos. X-ray binaries reveal stellar mass black holes actively feeding on companion stars. The cores of nearly every major galaxy harbor supermassive black holes that grew through billions of years of accretion and mergers. Every observation we've made, across every wavelength and every independent method of detection, confirms that the universe produces black holes readily and abundantly through well-understood gravitational collapse. Black holes have a birth story. We know how they form, we know the conditions required. We can point to specific processes in the real universe that produce them reliably and abundantly. White holes have no birth story. There is no known physical process that could create one. The full Schwarzschild solution that contains the white hole region describes an eternal geometry, one that has existed for all of time. The white hole doesn't form at some moment. It's simply there, eternally stretching back into the infinite past. But our universe is not eternal. It began with the Big Bang about 13.8 billion years ago. Before a certain point, the conditions that the eternal Schwarzschild solution assumes didn't exist. The universe was a hot, dense, rapidly expanding plasma, nothing like the static, eternal space-time the Schwarzschild geometry describes. When physicists model realistic scenarios, when they describe how matter actually behaves in the real universe with its real history and real initial conditions, white holes don't appear. The collapse of a massive star produces a black hole, not a white hole. The merger of two neutron stars can produce a black hole. The accumulation of gas at the center of a galaxy can feed and grow a supermassive black hole. There are multiple well-understood routes to creating a black hole. There are 0 well-understood routes to creating a white hole. Some physicists have tried to construct scenarios that could produce white holes. Could some exotic quantum process create one? Could a black hole somehow transform into a white hole at the end of its life? Could the Big Bang itself be considered a kind of white hole? We'll explore some of these ideas later, but the crucial point for now is that none of these proposals has gained mainstream acceptance. None of them is supported by strong observational evidence. None of them provides the kind of clear, testable, well-understood formation mechanism that black holes enjoy. Without a formation mechanism, a white hole is an orphan. It's a solution looking for a source. It's an answer without a question. The mathematics describes what a white hole would be, but the physics provides no explanation for how one could come to exist. The fourth argument is observational. We've never seen one. For decades, astronomers have surveyed the cosmos with instruments of increasing power and precision across the entire electromagnetic spectrum. We've built gravitational wave detectors, mapped the cosmic microwave background with exquisite precision, and catalogued billions of astronomical objects from nearby asteroids to galaxies at the edge of the observable universe. In all those observations, we have never found a single object that behaves the way a white hole should behave. We've never found an object that ejects matter and energy without any apparent source. We've never found an event horizon that works in reverse, repelling all incoming matter. We've never found a gravitational signature consistent with a white hole's predicted effects on surrounding space-time. Now, this argument by itself isn't decisive. Absence of evidence isn't always evidence of absence. Maybe white holes are very rare, maybe they're very small, maybe they're hidden in some part of the universe we haven't observed yet. Maybe they last for such a short time that they're impossible to catch in the act. But combined with the other three arguments, the lack of observations is powerful. If white holes existed, they would produce observable effects. They would eject matter and radiation. They would create distinctive gravitational signatures. They would stand out against the background of normal astrophysical objects, because nothing else in the universe behaves the way a white hole would. Consider the history of black holes for comparison. Black holes were predicted by general relativity decades before they were observed. For a long time, many physicists doubted they existed. Einstein himself didn't believe in them. But even before direct observations, there were indirect hints. Stars in binary systems orbited invisible companions too massive to be any known type of object. X-ray sources like Cygnus X1 emitted radiation consistent with matter falling into a compact, massive object with an event horizon. Gas at the centers of galaxies moved in ways that only a supermassive compact object could explain. The evidence accumulated gradually until black holes became accepted as real astrophysical objects. For white holes, the situation is reversed. There are no hints, no indirect evidence, no unexplained phenomena that could be explained by a white hole but can't be explained by anything else. Every bright, energetic object in the sky can be explained by known physics without invoking white holes. Quasars are powered by black hole accretion. Gamma ray bursts are produced by collapsing stars or merging neutron stars. Supernovae are the explosive deaths of massive stars. Active galactic nuclei are powered by supermassive black holes consuming gas. Every time astronomers have encountered an object producing enormous amounts of energy and matter, they've found a conventional explanation. No white holes needed. No white holes found. Taken together, these four arguments create a remarkably strong case. Thermodynamics says white holes are overwhelmingly improbable because they require entropy to spontaneously decrease. Stability analysis says even if one appeared, it would collapse almost instantly when exposed to the radiation that permeates all of space. The formation problem says there is no known physical process in the real universe that could create one. And observations say we've never found one despite decades of searching with ever more powerful instruments. Each argument alone would be concerning. Together they're decisive. The universe, it appears, has no room for white holes. And this brings us to perhaps the most important lesson of all. A lesson about the relationship between mathematics and physical reality. Because this lesson extends far beyond white holes. It goes to the heart of how physics works, and how we should think about the theories we use to describe the universe. Mathematics is the language of physics. Without mathematics, we can't make precise predictions. We can't build quantitative models. We can't test our theories against observation with the rigor that science demands. Mathematics is indispensable. It is the sharpest tool we have. But mathematics is a broader language than reality requires. Mathematical equations can describe things that exist and things that don't exist with equal facility. They can describe a ball rolling down a hill and a ball spontaneously rolling up a hill. They can describe heat flowing from hot objects to cold objects, and heat flowing from cold objects to hot objects. They can describe black holes and white holes. The equations themselves don't distinguish between what happens and what doesn't happen. They provide a menu of possibilities. The universe selects from that menu based on additional constraints, thermodynamics, initial conditions, stability requirements, quantum mechanics, that the equations alone don't include. This is why a solution to an equation doesn't automatically correspond to a real thing. You have to check. You have to ask whether the solution is consistent with all the other things we know about the universe, not just the particular equation that produced it. A solution that satisfies Einstein's field equations but violates the second law of thermodynamics is mathematically valid but physically suspect. A solution that satisfies the field equations but is unstable against the slightest perturbation is mathematically valid but physically irrelevant. A solution that satisfies the field equations but requires initial conditions that the universe never provides is mathematically valid but physically orphaned. White holes satisfy Einstein's field equations. They are valid solutions to one of the most successful theories in the history of physics. But they fail every other test. They violate thermodynamics. They're unstable. They have no formation mechanism. They've never been observed. The math says yes. Everything else says no. This doesn't mean general relativity is wrong. General relativity is spectacularly correct about an enormous range of phenomena. The bending of light around massive objects, the precession of Mercury's orbit, gravitational time dilation, gravitational waves, black holes, the expansion of the universe, all confirmed. All predicted by the same equations that also predict white holes. What it means is that general relativity is incomplete. It captures the geometry of space-time brilliantly, but it doesn't include everything. It doesn't include the thermodynamic arrow of time. It doesn't include the specific initial conditions of our universe. It doesn't include quantum mechanics. And when you add those things, when you combine general relativity with the rest of what we know about physics, the white hole solutions get filtered out. They exist in the mathematical landscape, but not in the physical landscape. This is actually a common situation in physics. Maxwell's equations, which describe electricity and magnetism, have solutions where electromagnetic waves travel backward in time, converging on a point rather than spreading outward from a source. These advanced wave solutions, as they're called, are mathematically perfect. They satisfy every equation, but we never observe them in nature because the initial conditions of the universe, the thermodynamic arrow of time, filter them out. Only the forward in time solutions, where waves spread outward from their sources, correspond to reality. Newton's equations of motion allow objects to spontaneously accelerate for no reason if you choose certain mathematical conditions. These solutions are valid, but they don't occur in nature because they require infinitely precise initial conditions that the physical universe never provides. Quantum mechanics has solutions where particles tunnel through barriers, and in principle, the equations allow for macroscopic objects to tunnel through walls. A baseball could quantum tunnel through a brick wall. The equations permit it, but the probability is so astronomically small, so far below any conceivable measurement threshold, that it effectively never happens. The math says yes in principle. Reality says no in practice. White holes belong in this category. They are solutions that the equations allow, but that the universe, for deep and well-understood reasons, does not produce. They are mathematically real and physically absent. They exist in the world of equations, but not in the world of stars and galaxies and space-time. And understanding this gap, this distinction between what the math allows and what nature does, is one of the most important skills a physicist can develop, because it applies everywhere. Every theory we have produces solutions that don't correspond to reality. The art of physics lies not just in solving equations, but in knowing which solutions to take seriously and which to set aside. In the case of white holes, the verdict is clear. The second law of thermodynamics says they represent an impossible decrease in entropy. Their horizons are so fragile that the ambient radiation of the cosmos would destroy them almost instantly. No known process in the universe can create them, and no observation has ever detected even a hint of their existence. They are beautiful mathematics attached to absent physics. They are ghosts in the equations, haunting the Schwarzschild solution like a reflection in a mirror that has no object standing in front of it. But that doesn't mean they're useless. Even solutions that don't correspond to reality can teach us something. Sometimes, the most interesting thing about a theory is what it predicts that doesn't exist. Because the absence tells us something important about the additional constraints the universe imposes on top of the theory. White holes teach us that general relativity, powerful as it is, doesn't have the final word. They teach us that the arrow of time, the second law, and the initial conditions of the universe are just as fundamental as the geometry of space-time. They teach us that physics is layered, that no single equation captures everything, and that the real universe emerges from the intersection of many different constraints working together. So, have physicists given up entirely? Have they thrown white holes into the wastebasket and moved on? Not quite. Because a few stubborn, brilliant thinkers have asked whether there might be loopholes, whether there might be special circumstances, extreme conditions, quantum effects that could somehow rescue white holes or produce something resembling one. And those speculative ideas, fragile as they are, deserve a hearing. We've built a strong case against white holes. Thermodynamics forbids them. Instability destroys them. No known process creates them. No observation has ever found one. By every physical measure, white holes appear to be mathematical ghosts, objects that live in the equations but not in the cosmos. And yet, a handful of physicists have refused to let the idea die completely. Not because they're ignoring the evidence. They understand the arguments against white holes as well as anyone, but because they've wondered whether there might be a special, extreme circumstances where something resembling a white hole could exist. Not as the eternal, idealized object from the Schwarzschild solution, but as something more subtle, more transient, more compatible with the physics that rules out the classical version. These ideas are speculative. None has achieved mainstream acceptance or direct observational support. But they're worth exploring because they reveal how physicists think at the boundaries of knowledge, where established theories run out and imagination must carry the work forward. And they reveal something deeper about what white holes teach us, even if they never exist. The first and most dramatic idea is this. Could the Big Bang itself be a white hole? At first glance, the resemblance is striking. The universe began approximately 13.8 billion years ago, in a state of extraordinary density and temperature. Everything expanded outward from a singularity where the known laws of physics break down. Now compare that to a white hole. Matter and energy emerge from a singularity, pass outward through a one-way horizon that nothing can cross going in, and expand into the surrounding space-time. Both involve eruption from a boundary beyond which physics offers no description. The parallels are obvious. Both involve a singularity. Both involve matter emerging from that singularity. Both involve expansion outward. Both involve a boundary where our physics breaks down. It's natural to ask whether the Big Bang is simply the universe's one and only white hole. A singular event of cosmic ejection from which everything we see today emerged. This idea has a long history. Physicists noticed the resemblance almost as soon as the full Schwarzschild geometry was understood in the 1960s. Some early cosmologists explored the possibility seriously. If the Big Bang is a white hole, they reasoned, then the mathematics of white holes might give us tools to describe the very earliest moments of the universe. But the idea falls apart under scrutiny. And it falls apart for several important reasons. First, the Big Bang singularity and a white hole singularity are fundamentally different kinds of singularity. The Big Bang singularity is a singularity in time. It's the beginning of time itself. There is no before the Big Bang, at least not in any way that standard physics can describe. Time starts at the Big Bang. The singularity is the first moment, the boundary of time's existence. A white hole singularity is different. It sits within a space-time that already exists. It's embedded in the larger Schwarzschild geometry surrounded by exterior regions where time flows normally. The white hole singularity is a feature within spacetime, not the origin of spacetime. It is a local object in a larger universe, not the birth of the universe itself. Second, the geometry of the Big Bang doesn't match the geometry of a white hole. The Big Bang is described by the Friedmann-Lemaître-Robertson-Walker metric, which is a completely different solution to Einstein's field equations than the Schwarzschild solution. The Friedmann-Lemaître solution describes a homogeneous, isotropic universe, one that looks the same in every direction and at every location. The Schwarzschild solution describes the space-time around a single, isolated mass. These are different mathematical objects describing different physical situations. The Big Bang isn't just a white hole in disguise. It's a fundamentally different kind of event described by fundamentally different mathematics. Third, the Big Bang has properties that a white hole lacks. The Big Bang involved the creation of space itself. Before the Big Bang, there was no space for matter to expand into. Space and time came into existence together. A white hole, by contrast, exists within a pre-existing space-time. It ejects matter into space that's already there. The Big Bang didn't eject matter into the universe. It created the universe. The distinction is not subtle, it's fundamental. Fourth, and perhaps most importantly, we have detailed observational evidence about the Big Bang that doesn't match white hole predictions. The cosmic microwave background radiation, the afterglow of the Big Bang, has been measured with extraordinary precision by satellites like WMAP and the Planck Space Observatory. Its temperature fluctuations, its statistical properties, its angular power spectrum, all of these match the predictions of standard Big Bang cosmology with remarkable accuracy. They do not match the predictions you would get from a white hole model. The data simply doesn't fit. So while the Big Bang superficially resembles a white hole, it isn't one. The resemblance is more like a visual analogy than a genuine physical connection. Both involve expansion from a singularity, yes. But the nature of the singularity, the geometry of the spacetime, the physics governing the expansion, and the observational signatures are all different. Calling the Big Bang a white hole is like calling a river a fire hose because both produce flowing water. The analogy captures something, but it misses everything that matters. The second speculative idea is more creative, and it comes from the American physicist Lee Smolin. Smolin proposed in the early 1990s an idea called cosmological natural selection. His hypothesis is remarkable for its ambition, even if it remains deeply speculative and unproven. Smolin's idea starts with a question: what happens at the singularity inside a black hole? We know that when matter falls past the event horizon and reaches the singularity, the known laws of physics break down, densities become infinite, curvatures become infinite. General relativity produces answers that include infinities, and infinities in physics usually mean your theory is failing, not that something literally infinite is happening. Most physicists believe that a complete theory of quantum gravity, a theory that unifies general relativity with quantum mechanics, would resolve these infinities. It would tell us what actually happens at the center of a black hole instead of just producing the answer infinity and shrugging. Smolin proposed that instead of a true singularity, the extreme conditions at the center of a black hole trigger the birth of a new universe. At the Planck scale, about 10 to the negative 35th meters, the collapsing matter bounces, but it doesn't re-expand back into our universe. It expands into a new region of space-time, a baby universe disconnected from ours, that inflates and evolves independently, developing its own stars, its own galaxies, its own physics. In this picture, every black hole is a seed. Every black hole that forms in our universe creates a new universe on its other side. And those new universes, if they develop black holes of their own, create still more universes. The result is a vast family tree of universes, each one spawned by a black hole in a parent universe. Now here's where white holes enter the picture. If a black hole in our universe creates a new baby universe, then the birth of that baby universe, as seen from the baby universe's perspective, looks like a white hole. Matter and energy emerge from a singularity and expand outward. The baby universe's Big Bang is, in some sense, the other side of a black hole in the parent universe. It's a white hole, not in our universe, but in the baby universe. This is an elegant idea. It connects black holes, white holes, the Big Bang, and the creation of new universes into a single framework. And it has a fascinating consequence that Smolin himself emphasized. If universes are born from black holes, and if the physical constants of each new universe are slightly different from its parents, then a kind of cosmic natural selection operates. Universes that produce lots of black holes create lots of offspring. Over many generations, the population of universes becomes dominated by those whose physical constants are optimized for producing black holes. This would explain why our universe seems finely tuned for producing complex structures like stars and galaxies and black holes. It's not coincidence, it's selection. But as elegant as this idea is, it remains unproven. There is no observational evidence that black holes spawn baby universes. We can't look inside a black hole and see what happens at the singularity. We can't detect baby universes even if they exist, because by definition they're disconnected from our space-time. The hypothesis makes some predictions. Smolin argued that our universe's physical constants should be near optimal for black hole production, and he claimed this is roughly true, but the predictions are vague enough that they're difficult to test rigorously, and even within Smolin's framework, white holes don't exist in our universe. They exist in baby universes, as those universes' big bangs. We would never observe one. We would never detect one. The white hole in this picture is always on the other side of an impassable barrier, visible only to observers in the baby universe who would see it as their own cosmic origin. For us, in our universe, white holes remain absent. The third speculative idea is perhaps the most technically grounded, and it comes from the Italian physicist Carlo Rovelli and his collaborator Hal Haggard. In 2014, they published a paper proposing that black holes might transform into white holes through quantum gravitational effects, but only after an extraordinarily long time. Their idea goes like this: a black hole forms from a collapsing star. It sits there for a very long time, slowly losing mass through Hawking radiation. Hawking radiation is the quantum process by which black holes emit particles from near their event horizons. The radiation is incredibly faint. A solar mass black hole would have a temperature of about 60 billionths of a degree above absolute zero, and would take roughly 10 to the 67th years to evaporate completely. The current age of the universe is essentially zero by comparison. But eventually, after this incomprehensible span of time, the black hole shrinks. It loses mass, it gets smaller and smaller, and at some point, when the black hole has shrunk to the Planck scale, to a size where quantum gravity effects become dominant, something dramatic happens. The collapsing matter that formed the singularity, which has been compressed for eons at the center of the black hole, bounces. It transitions through a quantum process from a black hole geometry to a white hole geometry. The matter that was trapped inside the black hole erupts outward in a burst of radiation and particles. The black hole has become a white hole. In Rovelli and Haggard's picture, this process is not instantaneous from our perspective on the outside. The quantum bounce at the center might happen very quickly in the reference frame of the collapsing matter. But because of the extreme time dilation near the singularity, the process takes an enormously long time as measured by outside observers. The black hole has to evaporate almost completely before the bounce becomes visible to the outside universe. Only then does the white hole phase manifest. And it manifests as a brief burst of energy, not as a permanent, eternal white hole of the kind described by the full Schwarzschild solution. This is a very different kind of white hole than the classical one. It's not eternal. It doesn't last forever. It's a transient event, a brief flicker at the very end of a black hole's incredibly long life. It doesn't violate the second law of thermodynamics in any obvious way, because the overall process, black hole forms, slowly evaporates, eventually bounces and releases its remaining energy, is consistent with entropy increasing overall. The white hole phase is just the final act, the last gasp, the moment when the information and energy that had been locked inside the black hole for trillions upon trillions of years finally returns to the universe. This idea is genuinely interesting. It addresses some of the deepest problems in theoretical physics, particularly the black hole information paradox. The question of what happens to the information about everything that ever fell into a black hole. If information is lost when a black hole evaporates, that violates a fundamental principle of quantum mechanics, which says information can never be truly destroyed. If the black hole bounces and becomes a white hole at the end, the information could be released in the white hole burst, solving the paradox. But there are major problems with this proposal too. First, it relies on a theory of quantum gravity that we don't yet possess. Rovelli's work is based on loop quantum gravity, one of several competing approaches to quantum gravity. Loop quantum gravity has not been experimentally confirmed. It's one possible framework, not an established theory. Other approaches to quantum gravity, like string theory, might give different answers about what happens at the center of a black hole. Second, the timescales involved are so enormous that this kind of white hole could never be observed. No black hole in the current universe has had time to evaporate significantly through Hawking radiation. The universe is only 13.8 billion years old. A stellar mass black hole needs something like 10 to the 67th years to evaporate. We're not even close. We would need to wait an almost unimaginable length of time before any black hole reached the stage where a quantum bounce could occur. By then, the universe would be unrecognizably different from what it is today. All the stars would have burned out. All the galaxies would have dispersed. The cosmos would be a cold, dark, nearly empty void. Third, even if the quantum bounce occurs, the resulting white hole burst would be incredibly small and brief. A Planck-scale white hole would release energy comparable to a large chemical explosion, significant by human standards but utterly negligible on astrophysical scales, far less than a supernova or gamma-ray burst. Detecting such a burst would be extraordinarily difficult even if you knew exactly where and when to look. So Rovelli and Haggard's white hole is theoretically possible within their framework, but it's an object that exists only at the very end of an almost infinitely long process, produces an almost immeasurably small signal, and relies on unconfirmed physics. It's the most physically plausible version of a white hole that any serious physicist has proposed, and even it sits at the very boundary of what we could ever hope to verify. Now let's step back from these specific proposals and think about what they have in common, because there's a pattern here that reveals something important. Every attempt to rescue white holes has had to dramatically modify the original concept. The eternal classical white hole from the Schwarzschild solution, the one that exists forever, ejects matter continuously, and has a permanently reversed event horizon, is abandoned in every serious proposal. Nobody tries to defend that object anymore. The arguments against it are too strong. Instead, physicists who are interested in white holes have been forced to look for loopholes. They've had to imagine white holes that are transient rather than eternal. White holes that exist only in other universes we can't observe. White holes that appear only after timescales so long that the current universe is a rounding error by comparison. White holes that are so small and so brief that detecting them would be nearly impossible. Each modification makes the white hole more physically plausible by making it less like a white hole. The more you adjust the concept to avoid the thermodynamic, stability, and formation problems, the further you get from the original mathematical object that the Schwarzschild solution describes. What you end up with isn't really a white hole in the classical sense anymore. It's something new, something different, something that borrows the name but discards most of the properties. This is revealing. It tells us that the problems with classical white holes aren't minor technical issues that a clever theorist might sidestep. They're deep, fundamental incompatibilities between the white hole concept and the way the universe works. You can't fix them by tweaking the details. You can only avoid them by changing the object so dramatically that it barely resembles the original. And this brings us to the deepest lesson of all. The lesson that white holes teach us about the nature of physics itself. Because even though white holes almost certainly don't exist, even though the arguments against them are overwhelming, even though every attempt to rescue them has failed to produce a convincing, testable, observationally supported theory, white holes are not a waste of time. They are not a dead end. They have taught us something genuinely important about how the universe works, and about the relationship between our theories and reality. The most important thing white holes teach us is this: mathematical elegance is not enough. A solution can be beautiful, symmetric, self-consistent, and elegant, and still be physically meaningless. White holes are the perfect illustration of this principle. They arise from one of the most elegant and successful theories in the history of science. They satisfy every equation perfectly. They exhibit a breathtaking time reversal symmetry with black holes. As pure mathematics, they're flawless, and they almost certainly don't exist. This matters because physicists are human, and humans are attracted to elegance. We find symmetric solutions beautiful. We're drawn to completeness. When a theory produces two solutions, one for each direction of time, there's a powerful aesthetic pull to accept both. It feels incomplete to accept the black hole and reject the white hole. It feels arbitrary. It feels like you're ruining the symmetry of the equations. But the universe doesn't care about our aesthetic preferences. The universe operates according to principles that include but go beyond the equations of general relativity. Thermodynamics breaks the time symmetry. The specific initial conditions of our universe select certain solutions and reject others. The stability requirements of physical systems filter out objects that can't survive contact with the real environment. Beauty isn't wrong, but beauty alone isn't sufficient. Physical reality imposes constraints that mathematical beauty doesn't capture. This lesson echoes throughout the history of physics. There have been many beautiful theories that turned out to be wrong, many elegant solutions that didn't correspond to reality, many symmetric frameworks that nature chose not to use. The lesson each time is the same. Mathematics is a powerful guide, perhaps the most powerful guide we have, but it must be checked against observation, against experiment, against the full body of physical knowledge. A theory earns its place not by being beautiful, but by being right. White holes also teach us something about the arrow of time. General relativity doesn't have a built-in arrow of time. Its equations work equally well forward and backward. But the universe does have an arrow of time. The second law of thermodynamics gives time a direction. Entropy increases, disorder grows, the past is different from the future. This arrow of time is not contained in general relativity. It comes from somewhere else, from statistical mechanics, from the initial conditions of the Big Bang, from the overwhelming mathematics of probability applied to vast numbers of particles. White holes are what you get when you ignore the arrow of time. They're what the equations produce when you treat forward and backward as equivalent. But the universe doesn't treat them as equivalent. The universe has a direction, it has a before and an after. It has a past of lower entropy and a future of higher entropy. White holes are backward in time, and the universe doesn't go backward. Understanding why the universe doesn't go backward, understanding the origin of the arrow of time, is one of the deepest unsolved problems in physics. Why was the early universe in such a low entropy state? Why did the Big Bang produce such ordered initial conditions? We don't know. This is an active area of research, but whatever the answer turns out to be, white holes will be part of the story, not as objects that exist, but as objects that don't exist, and whose absence tells us something crucial about the nature of time. Finally, white holes teach us about the limits of general relativity. General relativity is one of the most successful theories ever formulated. It has passed every experimental test we've thrown at it. It predicts phenomena, gravitational waves, black holes, the expansion of the universe, with stunning accuracy. But it is not a complete theory of everything. It breaks down at singularities. It doesn't include quantum mechanics. It doesn't know about entropy. And it produces solutions like white holes that the rest of physics rules out. This tells us that general relativity, magnificent as it is pointing towards something larger. Something that includes everything general relativity gets right, but also includes the thermodynamic arrow of time, the quantum behavior of matter and energy, and the stability requirements that the physical universe imposes. That larger theory, the theory of quantum gravity, is the great unfinished project of modern physics. We don't have it yet. We have candidates, loop quantum gravity, string theory, and others, but none has been confirmed. When that theory arrives, if it arrives, it will answer questions that general relativity cannot. What really happens at the singularity inside a black hole? What were the true conditions at the Big Bang? Is time reversal possible at the quantum level? And perhaps, do white holes play any role in the deep quantum structure of space-time? Until then, white holes remain what they have always been. A mirror that general relativity holds up to reality, showing us a reflection that's mathematically perfect, but physically absent. That mirror teaches us something not about what exists, but about what doesn't exist, and why. And sometimes understanding what doesn't exist is just as important as understanding what does. Because in the end, the universe is not obligated to be symmetric. It's not required to produce every object that its equations allow. It's not bound by our aesthetic preferences for completeness and elegance. The universe is what it is. It follows its own laws, including laws that general relativity alone doesn't capture. And when we listen carefully to what the universe is telling us, when we pay attention not just to the equations, but to the observations, the thermodynamics, the stability, and the history of the cosmos, we hear a clear message. Black holes are real. They form from dying stars. They sit at the centers of galaxies. They merge and produce gravitational waves. They are among the most remarkable objects in the universe. Objects where space-time curves so dramatically that nothing can escape. White holes are their mathematical twins, born from the same equations, exhibiting the same geometry in reverse, possessing the same elegant mathematical structure. But twins separated at birth, one raised by the real universe, shaped by thermodynamics and initial conditions and the relentless arrow of time. The other left behind in the world of pure mathematics, beautiful and perfect, and almost certainly alone. The universe chose the black hole. It rejected the white hole. And understanding why it made that choice tells us more about the deepest nature of reality than the white hole itself ever could. So the next time you hear someone ask what a white hole is, you can answer with confidence. A white hole is the time-reversed counterpart of a black hole. It appears naturally in the mathematics of general relativity. It would eject matter and energy through a one-way boundary that nothing could ever cross going inward. It would be the strangest object the universe could contain. And it almost certainly doesn't exist, because the universe imposes constraints that pure mathematics doesn't capture. Thermodynamics, stability, formation history, and observation all point in the same direction. The equations allow white holes, the universe does not, and that gap between what the equations allow and what the universe permits is one of the most fascinating, most humbling, and most instructive spaces in all of science. It's the space where we learned that nature is richer and more selective than any single theory can contain. It's where we learn that physics is not just mathematics, but mathematics filtered through reality. And it's where we learn again and again that the universe has surprises waiting for us. Not in what it creates, but sometimes in what it refuses to create. Thank you for joining me on this journey through one of the strangest ideas in all of physics. If you found this exploration valuable, a like or subscribe would mean a lot. It helps me keep making these deep explorations of the cosmos. And remember, the next time you look up at the night sky and think about the black holes lurking out there in the darkness, invisible and immense and utterly real, spare a thought for their mathematical twins. The white holes that the equations demand, but the universe denies. They're out there in the mathematics, perfect and symmetrical and beautiful. And they're nowhere in the sky. That absence is itself a kind of answer. An answer about the nature of time, the direction of the cosmos, and the deep, selective, astonishing logic of the universe we call home. Good night.